Okay, I think we'll get started here. So it's a pleasure to have Holger Mueller from Berkeley visiting us today. Holger did his PhD at Humboldt University with Occam Peters before moving on to Stanford as a postdoc as a Humboldt Fellow with Steve Chu. Holger was sort of kept in California, where he's now at Berkeley, as I said. And he's a world leader in using interferometers composed of light or atoms for precision measurements. His work has been recognized for multiple different awards, including being a Packard Fellow and also a Brown Investigator more recently. Today I'll be telling you about work that he's doing, which is really world leading in preparing interferometers, atom interferometers that allow for atoms to be trapped and coherently delocalize over really, really long timescales, which are critical for doing precision measurements of things like gravity. So with that, I will.
Thank you so much. Thanks for the invitation. Okay. Minute scale coherence in an atom interferometer, or to steal a line from Rainer Blatt, keep the quantum state alive. I'll start unconventionally with thanking the people. So the experiment was, the results I'm going to talk about were in large part done by Chris Panda, who is now setting up at University of Arizona. The current grad students are Matt Tao, Garrett, Louis, and James, who is somewhere in that picture. Where is James? Whatever. And they are just a great team, as you shall see. OK. Interferometers. I don't need to talk much about that, but here's the LIGO Gravitational Wave Observatory. They have arm lengths of 4 kilometers that they extend further to an effective length of 400 kilometers by having the beam bounce back and forth inside a Fabry-Perot cavity. When the two beams recombine on the photodetector, then a half wavelength shift in the arm length relative to one another makes the interference go from destructive to fully constructive, where the entire laser power would hit the detector and burn it out, presumably. So since the arm length is 400 kilometers, that's about 1 billion wavelengths, OK? So 1 part per billion arm length change causes 100% change in the signal on the detector. In that sense, an interferometer gives you a giant lever arm to turn a tiny effect that you want to measure into a large change of your photon count on the detector. That's what it does. OK. And an atom interferometer is very much the same thing, except that now our source of waves is a source of cold atoms. It doesn't have to be a Bose-Einstein condensate. In fact, there's some ins and outs that make it complicated to use BECs, so we don't do that. And the beam splitters are actually laser pulses, not mirrors. So a photon hits the atom, and if it gets absorbed, then it also transfers the momentum, h bar k, to the atom. We use 2 photon processes which drive the atom via an excited state back to the ground state that avoids some sources of decoherence and doubles the momentum transfer. So the atom arrives here, and if it does get kicked up, then it moves upwards with a velocity that's higher by 2 photon momenta, or it stays on the path. Then after time t, we flash the laser on again, kicking the lower arm up and the upper arm down. And after time 2t, we flash the laser a 3rd time, recombining the 2 wave packets. And again, the number of the phase shift along each arm can be very, very large, in the tens of millions, even billions of radians, so that a tiny shift in the phase shift generates a large change in the probability of detecting atoms in either output of the interferometer. Here is some modest experimental data taken with our machine, where we just vary the effective acceleration of gravity. That's done by applying a phase modulation to the laser beam. And you see the sinusoidal variation of the atomic population. So none of this is new and has been used in many, many experiments. For example, what does this phase difference that we're very sensitive to depend on? Well, the phase shift accumulated by a matter wave going along a path is proportional to the action of the particle evaluated along that trajectory, okay? And that action includes the effects of gravity, so you can measure the acceleration of free fall with an atom interferometer, or you put some test masses close to the interferometer and make a measurement of the gravitational constant, here done by Giammattino and Florence. Markasevich has separated the two wave packets by as much as 0.5 meters and still obtained interferences, and that tells you something about the validity of quantum mechanics on macroscopic scales. And at Berkeley, we've measured the fine structure constant with an atom interferometer. So let me talk about that a little bit. But before I do it, let me give you another application of atom interferometry that's actually done with a very simple atom interferometer. So we built one that was about the size of a refrigerator and had wheels. So we wheeled it into a U-Haul truck that we rented at U-Haul and drove it through the Berkeley hills, which are not quite as tall as the Rocky Mountains, but still tall. And so as you go up the hill, little g goes down as expected because you move further away from the center of the Earth. At the same time, however, it does not go down as fast as you would expect if you were moving up in vacuum, because the density of the rocks in the hills pulls you down. And in fact, the density of those rocks can be extracted from that data. When the setup was resting in the lab, it took this data over some time. Little g seems to vary. That's the influence of the sun and the moon, also known as the tides, right? So you see they go up and down, up and down. And these can be modeled very well because we allegedly know where the sun and the moon is. And then you subtract a tidal model, and you see that the tidal model is not quite right. Why is that? It's because of the San Francisco Bay, which so the water rushes in and out with the tides, right? But unfortunately, the mass distribution in the San Francisco Bay is particularly hard to model because the bay is not, to first approximation, like a swimming pool with a clear separation between water and land, but it's more like a mud. You don't really know where the water begins and the land ends. That makes it very hard to model, hence the residuals. So you can turn it around and learn something about the bay from this data. Another thing that we became aware much later is that inside this data, there were hidden two earthquakes. One was in South America, and the other one was in Asia. I don't remember which is which. So we were working with some geophysicists who made us aware of that feature much after the fact. All in all, even this very primitive atom interferometer, this by no means state of the art, it's a very simple one, is sensitive enough to take all this nice data. This was published in Science Advances and is actually quite well cited. Why is that? Because there were many people also building mobile gravimeters, but they did not go to U-Haul and rent a truck and drive it around the hills close to their university. So that was also a nice adventure. Yeah?
Yes, so in the first example, you talked about either the tree or the hole. Is that the
So with atoms, I know of three ways. One is light pulses, like we used. And then there is gratings made of materials, like ruled gratings or something like that. And the third one is the Stern-Gerlach effect. And they have all been tried. So which one do you use when? So I will only talk about light pulses, and the great advantage here is that you know the momentum transfer to high accuracy from the wave number of the photons, which as opposed to the Stern-Gerlach effect, where the separation will depend on the strength of the applied magnetic field gradient or the spacing, the lattice constant of a man-made grating, right? So the nice thing about light pulses is you know the momentum separation to high precision, but the other methods have been used. Yeah. Yeah. So I was trying to avoid talking about. Oh, no. These are absolutely valid questions. So I don't have a slide about that, but here, let me start with, let's say the atom, let's model it as a two-level system, has a ground state and an excited state, and let's assume that the excited state lives very long and doesn't decay. This is not the case in our experiment, but for the, just bear with me, okay? Then if you shine in a resonant laser and give it the correct, give it a constant intensity, it will Rabi flop between being in the ground state and the excited state. So the probability that it's excited is a sine squared of time. And in order for us to generate the superposition, we stop that when it's at the 50-50 point. Okay. Unfortunately, it's not that easy in reality because our excited state decays quickly. There are people in this room who work with strontium and ytterbium, which does have extremely long-lived transitions, and with those atoms, you can do it that way. What we have to do is we have to, the ground state is actually, there's a whole manifold of states. For example, there might be different hyperfine levels, or there are separate levels that are the atom being in the same internal state, but just moving with the momentum of 2 photons, 4 photons, 6 photons. So that gives you energy levels that are split by just several kilohertz. So what we do is we shine in a first laser that drives the atom up almost to the excited state with some detuning that prevents propulating the excited state. And a second laser stimulates the atom down to one of those other ground states. And because we never actually reach the excited state, we're not subject to that decoherence. And the third thing you asked, isn't there a problem with the atom coming out in several different states? And the answer is yes, there is. And in particular, when you use Bragg diffraction, which we often do, and then it's a complicated interplay between the pulse shape and the pulse duration that we need to get right in order to make sure the atoms all come out in the same state. One of the leading experts in how to shape the pulse is here. So you could, we can talk about more of that later, but thanks for the question. You discovered an important gap in my talk. Okay, dropping atoms, applications. The fine structure constant. Yes. Okay. How would I even measure the fine structure constant with an atom interferometer, right? So I can measure the fine structure constant with hydrogen spectroscopy because the Rydberg constant is essentially 1/2 MEC squared alpha squared. Okay. So if I know the Rydberg constant, and I can ask my favorite hydrogen spectroscopist what the Rydberg constant is, and then I ask someone who magically tells me what the electron mass is, right? Then I can solve for the fine structure constant. Unfortunately, the person who can tell me what the electron mass is does not exist because the electron mass is extremely well known in atomic mass units. But in order to apply that equation that I just outlined, I need to know it in kilogram. And that's not so well known. So what we do is we measure the mass of an atom in kilogram with the atom interferometer. And then we ask our friend, what is the mass of the cesium atom in atomic mass units and the one of the electron in atomic mass units? And then we can solve for the fine structure constant. So I'm hitting my atom with a photon. It recoils with the momentum of 2 photons. In actual fact, we use 10 photons to boost our signal a little bit. And then we measure that kinetic energy, which is now a measurement of the mass of the cesium atom if I know the momentum. And we'll have to talk more about that later. Okay? And then I solve for alpha. So this is a picture from our lab from the old fine structure constant experiment. Why would I want to do that? Because then I can give the number to the theorists, and they can use it to calculate yet another number, which is the electron's gyromagnetic anomaly. The electron's magnetic moment in Bohr magnetons is a bit more than 2. That's the anomaly. And that difference has been calculated to more than 10 decimal places of accuracy. okay? And then Jerry Gabriels has measured G-2 to a commensurate accuracy. And so we have the unique situation that a number that can be measured to 10 decimal places can be plugged into a theory that's valid to similar precision. And the prediction can be compared to another experiment, which again has more than 10 decimal places accuracy. So that's a unique, often the things you can calculate very well aren't that well measurable, or the things you can measure very well cannot be calculated very well. But here it all comes together and makes for one of the most accurate tests of the standard model. At the current accuracy, we have to go to fifth order QED involving more than 10,000 Feynman diagrams. We have to account for the existence of the muon. We have to account for the existence of virtual hadrons. And this is the bad part, because this cannot be calculated perturbatively and is actually the subject of a controversy. Okay, and then if all of that works out, then the number measured here predicts the number measured here, and all checks out, right? So this is great. The thing is, it doesn't really check out that well. For one, the muon magnetic moment continues to disagree from the standard model prediction, and the controversy here is, depending on which model you use for calculating those hadronic influences, you can actually make it agree fairly well, okay? So the question is now, in a sense, you could interpret that as a test of which way of attacking the hadronic terms is the more correct one, but I'll leave that to the theorists. All I say is that not all is well with theory, the experiment comparison with lepton magnetic moments. With the fine structure constant, it's a similar dilemma. So before our measurement, this was the best atomic physics measurement done in Paris with rubidium atoms. And this was the number deduced from the electron's gyromagnetic anomaly. And then the measurement we did, published in 2018, the error bar overlaps completely with the one of the Paris measurement. So that's great. There's a slight tension with the one obtained from the gyromagnetic anomaly, but nothing to get really worried about. So we were really happy about this result. And I should mention that Joyce was involved in that measurement, who is now a postdoc here. It's a small world. But then the Paris measurement built a new setup, again with rubidium, and came out with this value. And there is now quite some tension between these two values. So that's bothering us. I wish I could tell you, yeah, it's very obvious that our measurement is right? But I can't, because they have really done a careful job. There's nothing in here where I could say, yeah, this is probably the reason for the discrepancy. So long story short, we have to measure this again to find out what the fine structure constant really is and what might be responsible for the discrepancy. Our main suspect is, if you look at the error budgets of the Berkeley experiment and the Paris experiment, it is the fact that the laser beams are not exactly plane waves. So I mentioned you need to know the photon momentum, and that's, of course, h bar k. And then you think, well, k is omega over c, very easy. And omega I measure with a frequency comb, and I'm done, right? Except that the latter relation, k is omega over c, is only true for a theoretically perfect plane waves. And real laser beams aren't perfect plane waves, so k is slightly different from omega over c. In fact, it's different at every point in the beam. So now I need to know what is the exact shape of my laser beam, and where exactly are the atoms relative to the laser beam, right? And so, of course, both experiments try to determine these pieces of information and apply a correction to the data. And these corrections are the largest items in the error budget, both in terms of the absolute size of the correction applied and in terms of the uncertainty of the correction. So if you ask me, make a guess, where can we find the reason for this discrepancy? I would say it's in the shape of the laser beam. It's a guess until we've tried it, but it's our best guess. So our new experiment has a large diameter vacuum chamber, because one of the nastiest distortion deviations of a laser beam from a perfect plane wave is when it's scraping the wall. Okay, that creates virtually unpredictable distortions of the beam. So we're now making sure that the beam is not scraping the wall by moving the wall far away from the center of the laser beam. It's blackened inside to prevent scattering. It has baffles to further prevent scattering. It has large diameter optics everywhere to prevent aperturing at the other optical elements. And in addition to that, there's quite a bit of modeling involved in determining the corrections, right? You need to model how the atoms move. You need to model how the laser beam propagates. So these models should be compared directly to data. So what we're now doing is we're inserting amplitude and phase masks into the beam to distort the beam in a known way. And then we try to predict the effect of those distortions on the data. And then we compare theory and experiment. So our lines of attack are reduce the deviations of the laser beam from a perfect Gaussian beam, okay? And second, test the models that account for the residual deviations. And that hopefully gives us a more reliable measurement of the fine structure constant and eventually will allow us to see what the fine structure constant is. This is all very nice, but let me come closer to the central topic of the talk. All these experiments would love to have a very long interaction time with the atoms, and people have gone to great lengths to improve that. Famously, in Stanford, they have set up a 10-meter atomic fountain where they can get up to close to 3 seconds of full experiment time before the atoms hit the wall, right? They have dropped a BEC inside a drop tower. They have flown an atom interferometer on zero-G flights, and they have even put an atom interferometer on the International Space Station. Now, in all these 3 experiments, the interaction time is not limited by free fall anymore, but instead by things the vacuum chamber size, atom losses due to background gases, and vibrations. And the best that people did so far is in Stanford with 2 or 3 seconds, right? But what if you wanted to do 10 times more than that? Well, then you'd have to make this 100 times taller, and that's pretty much impossible. So, but why do you want even longer coherence times? And the answer is because I want to find out whether gravity is a quantum interaction. And why do you want to do that? Well, the first thing is, how long? Let's ask the very basic question. I borrowed this argument from Jake Taylor. So Jake Taylor essentially asks himself, how long do I have to have my interaction working so that gravity can be the dominant effect on a quantum system? So here is a purely gravitational system digging a tunnel through the center of the Earth and jumping in, right? And if the Earth were a constant density, you'd be performing harmonic oscillations with a period proportional to 1 over square root g rho, where rho is the density, and a few factors of 2 pi, right? So this 1 over square root g rho works out to 15 minutes for the density of tungsten, which is one of the densest materials that can be found on Earth, right? This is a necessary condition, not a sufficient condition, right? But 15 minutes is roughly the period of a gravitational harmonic oscillator. So if I can keep my quantum state coherent for that long time, then I can devise an experiment in which gravity is the dominant interaction. If, on the other hand, the quantum system is not coherent for 15 minutes, then I know that there is some interaction that's stronger than gravity decohering it, right? So this is a necessary condition, not a sufficient one. And of course, it's a hand-wavy condition, right? It's not that 14.9 minutes is insufficient, but 15.1 is sufficient. It's a gradual thing. But at least many minutes of coherence time would make really good gravitational experiments with quantum systems. So the only way to achieve that is to hold the atoms for a long time. So this is not our idea at all. As far as I know, it's due to Pierre Cladet, who was actually involved in the French alpha measurement also. And the first realization, as far as I know, was done at Onara, which is a French aerospace lab just outside of Paris. And they used a standard laser pulse as a beam splitter for a set of rubidium atoms, and then another laser pulse to make the relative velocity of the two wave packets 0. And then you just wait for gravity to bring them to a halt. Then you turn on your optical lattice, a periodic potential that you can use to hold these matter wave packets, similar like in bookshelves. And after the hold time is elapsed, you turn it off and you reverse the beam splitting sequence to put the wave packets back together. At Onara, they got this to work to several hundred milliseconds, and then Gelmutino in Florence increased it to 1 second. But 1 second isn't any longer than what you can do in atomic fountains. So my prime suspect, again, was laser wavefront distortions, maybe the reason for this loss of coherence. And so we put the whole thing inside an optical cavity to make the laser beam a better Gaussian beam and see how far we get. So here's the apparatus. The cavity is about this long. The cavity mirrors, so can't really see. There's a vacuum chamber and a lot of optical mounts surrounding it and magnetic coils. So there's a science chamber in the middle where we try to get the vacuum to really good values. The mirror mounts might be outgassing a little bit, so they are in extra vacuum bulbs with some differential pumping in between. That way we can get a better pressure here, even though the mirror mounts are outgassing a little bit. That's 10 to the 6 cesium atoms in the lattice, roughly. The finesse is not all that large because we need to be able to slightly vary the laser frequency without running away from the resonance too much. Our first application actually wasn't taking advantage of the cavity at all. I was talking to Helmut Rich at the time, and he said, we've predicted that black body radiation should cause an effective attractive force on atoms. So here's how that works. Room temperature black body radiation is mostly infrared, so it's redly tuned to atomic transitions. That means it creates a negative AC Stark shift of the ground state, which means the atoms have a tendency to go into the region of the strongest black body radiation. And that creates an attractive force generated by warm objects in the vacuum chamber. Okay, this force is surprisingly large. So we put some metal object inside that we can heat up by a laser from the side. And then we measure the acceleration as the mass cools down. And in order to suppress systematics, we toggle the mass from being near and far, right? So measure only the difference of the two. And then you can make this plot, which gives you a nice T to the 4 curve, where the acceleration in microns can be up to the micron per second square level. And that is really jarring for a community where we claim that we measure nanometer per second square routinely, right? So how come we could have overlooked such a huge effect? And the answer is, if the temperature of your setup is homogeneous, then this force is 0. But what it means is if you really want to be accurate, you need to make sure your temperature is homogeneous. And so people in all kinds of atom interferometry labs started installing temperature sensors all along their vacuum chambers. So that was a first application. A second one was testing a model of dark energy called the chameleon. And I don't have time to get into that. What it essentially is a scalar potential that's characterized by 2 parameters. One is called M, that characterizes how strongly it couples to local matter, and lambda, which gives a self-interaction. Okay, and for lambda, there's a preferred value here at 2 millieV given by the cosmological dark energy density. Anyway, people found limits on the existence of such particles in all sorts of experiments. For example, Giorgio Gratta and his trapped microspheres. Neutron interferometry used to be the leading method, and then atom interferometry this was our 2015 paper, and this was our 2017 paper, really cuts deeply into this parameter space. And I have to highlight that the idea of doing so is due to Claire Burrage and Ed Hines at University of Nottingham and Imperial College in London, respectively. So these were two satisfying results with the cavity interferometer, but they did not actually take advantage of lattice hold. So it's high time to turn on the lattice hold. And when we did that in 2018, we were really, really happy to see 1 second and then 5 seconds. And I thought, oh my God, this is working so much better. But the students pushed it out to even 20 seconds. And you can still see a little bit of a fringe here. OK. So that made us, that really worked beyond expectation. For example, you could ask your, no, let's not do that. We don't have enough time. But there's all sorts of reasons why you might believe that the coherence would decay way faster than observed here. So suffice it to say, I would have written a PRL at 2 seconds, and at 5 seconds, I would have thrown a party. But 20 seconds, I did not expect. Great. But what is it useful for? Well, one thing it's useful for is if you take this whole optical table and tilt it a little, then with a standard atom interferometer, what will happen is you have now turned your laser beam so that it's no longer parallel to local G. And so the atoms will just fall out of the laser beam, and your atom interferometer will stop producing data. That's one of the main reasons why atom interferometers have not been used in the field as gravimeters very much, because they are so sensitive to even minor tilts. The lattice interferometer holds the atoms in place, and so a small tilt just causes it to measure the projection of gravity onto its new symmetry axis, which you can see here. And then you only need a modestly accurate tilt sensor in order to correct for that, and you can still get your data. That means you're now no longer required to keep it exactly vertical. We've also measured the dependence, the sensitivity to accelerations and vibrations. Now, there's a thing to be said here about the equivalence principle, which says the effects of gravity are the same as the ones of being in an accelerated frame, right? For example, a vibrating lamp. So if you want to measure gravity, you're automatically sensitive to vibrations. It's unavoidable. But you can be more sensitive to vibrations than required by the equivalence principle. And that is the case with atom interferometers, because imagine that you run your atom interferometer for a second while your apparatus is shaking, right? The best you can do to measure gravity during this 1 second is to average over the vibrations. But a pulsed atom interferometer does not average. It pulses, and therefore it aliases the vibration, which folds a lot of high-frequency noise into the baseband, and you get more noise than required by the equivalence principle. Whereas, if you hold the atoms, you couple them to the vibrating reference frame all the time, and you get a nice averaging. So we calculated that, and we actually shook our table with a loudspeaker drive, and we could measure this data that shows, yeah, the noise suppression really works. And this is the equivalent curve for standard atom interferometer that has the same sensitivity at DC. So you're now a lot less sensitive to vibration. This, and we also showed that this can work. We turned the mod coils back on while the interferometer was running. And you see that you Zeeman split your data, but the average of the two is constant. So you now can measure gravity under real-world conditions, for example, on a ship, and you can do things like gravity-assisted navigation and so on. So this is really useful in practice. Okay. But now we're physicists. We want to know, OK, we're really happy about those 20 seconds, right? But we also want to know, why is it 20? Why is it not 10? Why is it not 30? And that was really a hard nut to crack. So very early, we, of course, plotted this, the contrast as function of hold time, and it looks like it decays exponentially with a time constant, tau c. And that time constant, we could also fit our data, is inversely proportional to the lattice depth, so a shallower lattice is better, and to the splitting between the wave packets. Less splitting is better. So here's data with different splittings and different trap depth, and a global fit to that data puts that constant at about 110 seconds for 1 micron of splitting and 1 recoil of lattice depth, right? So you ask, why don't you just turn down your lattice depth? Because we need about 5 to 10 recoils of depth to prevent the atoms from falling, right? Okay, so that became clear early on, but then we wanted to improve this, and it turns out almost everything we tried yielded exactly 0 effect. Our first guess was, well, if a cavity helps improve this from 1 second to longer time, then maybe a better cavity helps. So we used much better cavity mirrors, much better polished, and so on. And that made exactly 0 difference. Then we thought maybe it's the fact that the laser beam has a waist somewhere, and we need to have that waist at the center of the splitting between the wave packets. And that made exactly 0 difference. We checked things like replacing lasers by other lasers, changing laser wavelength, and so on. And there was always no change, no change, no change, no change. Chris Panda, the postdoc, is the hero of this. He spent the major time of the pandemic going through this list and depressingly finding nothing. Until we narrowed the lattice radius by exciting a higher order lattice mode. So the Gaussian 0,0 mode of the cavity looks like this, and then there's a Laguerre Gaussian mode that has a narrower peak in the middle and some wiggles outside. And effectively, the atoms will only see that narrow peak because the atoms that are far away from the peak fall away. And what the sheer observation is that using this narrower mode improves this contrast decay constant by a factor of about 3. Now the question is, what does that do? One thing it does is, after atom preparation, the atoms start expanding, and then we turn on the lattice and capture the atoms that are still inside the radius of the lattice. Well, if I narrow the lattice, then I'm capturing only the part of the population that moves more slowly. So we have a colder subset of atoms now. Maybe that's the reason. And to test that, we used the narrower lattice only for capturing the atoms and then switched back to the larger diameter lattice, and we saw the same improvement. So we now knew that atom temperature had to be part of the equation. Another thing we found is that tilt noise, when the lattice shakes around due to vibrations of the lab floor, is part of that. Now, of course, we modeled the whole thing. So we Monte Carlo'd the system with Gaussian lattice potential, taking into account Landau-Zener tunneling, taking into account vibration of the lattice, and so on. And then we get pictures like that that do reproduce the initial roughly exponential decay of the contrast with time. But what it also does, it predicts a new regime where some contrast, small amounts of contrast, but not 0, should persist for up to a minute. Okay, and we ran the simulation with more atoms and so on to make sure that this is not just the noise of the simulation. So we were convinced that the same model leads us to expect a small amount of contrast for a much longer time. Why is that? Because the fastest moving atoms move away from, just drop out of the lattice first, and then after 20 seconds, only a colder subset is left behind that should generate this tail of lasting low-level coherence. As a small interlude, you might ask, well, vibrations are bad, I knew that. Hot atoms are bad, I knew that too, so what took you so long, right? So the first thing that took us so long is that we had this data we were proud of that showed that linear vibrations were really not a problem, that it was in fact one of the strengths of our setup to be insensitive to linear vibrations. And being human, we concluded that we would no longer have to look into the issue of vibrations, right? That's one thing. The other thing is atom temperature alone is actually harmless. A hot atom will orbit around in the trap, okay? But then you beam split it. Now you have two partial wave packets orbiting around in the trap. But if the lattice here and here has the same potential, then this orbit is harmless. It does not generate a relative phase, right? But if I have this orbit and the lattice potential is different between here and here, then I get dephasing. And such a difference is induced by tilt noise of the lattice, because now the two lattice sides are at different distances from the pivot point. That is the major thing. We convinced ourselves earlier that making the cavity mode more symmetric with respect to the interferometer had no effect, right? That's another thing that biased us against realizing that this asymmetry is the cause, because we had tested one type of asymmetry and found it to be harmless. So we assumed that all kinds of asymmetry are not important. Anyway, we were happy to have this data, and now we wanted to see, can this be detected, right? So in order for detecting this predicted very small amount of persistent contrast, we had to improve the signal to noise. So we improved the atom number. We reduced atom losses by larger detuning of our lasers. We improved the lattice amplitude to a much higher to stabilize the amplitude to a much higher degree to eliminate or reduce parametric heating, lower noise detectors, and so on. And that beat the noise down to about 1 to 2 times the standard quantum limit. And indeed, those long-lasting coherences could be observed. They are not large, that is expected, but they are significantly non-zero. Cool. Okay, so here's the same data plotted in a different way. The blue line is an exponential decay fitted to the initial 20 seconds. And you can see that fits well for 20 seconds and then goes down. The arrow bars are the actual data. And this double line is the significance region of the Monte Carlo model. So you can see that this is actually in fair agreement with the model. Also, what it shows is if I now, in the model, I can make any kinds of assumptions. For example, I can assume that I start with an extremely cold ensemble. Then I would get a decay like that. So I would have this very slow decay, but starting around here. So if I could rebuild the experiment with a BEC machine as my atom source to have a significantly colder sample, then I would expect better coherence. Or if I could rebuild the experiment with significantly better vibration isolation to remove the tilt noise, then I could expect better coherence. And that's, in fact, what we're doing now. Before I show you that, quick look at systematics. Let me skip over that very quickly. Of course, the reason you don't want the laser on all the time is that the laser introduces systematic errors. So can you perform a measurement despite these systematic errors? And there, Chris Panda, the postdoc, adopted a page from the ACME playbook, the the cold molecule EDM collaboration, right, where they apply switches to their system. And the switch, so we're trying to measure, again, the gravity of the tungsten mass here on our atoms. Here's a movie of the atoms and the tungsten mass. And so what we want to do is toggle the atom position between top of the mass and bottom of the mass, reversing the attraction of the tungsten mass, and toggle the mass position from close to the atoms and far away. And when you do that, you get 4 measurements, right? Mass in, mass out, atoms top, atoms bottom. And only one combination of those 4 measurements is the signal you want to measure. The other 3 combinations give you monitors about the health of the experiment. And we did that, took data for 2 months. The data has a noise floor just a little bit above the SQL, has a good chi-squared value. We did systematic checks. The systematic uncertainty was about 5 times lower than in our previous implementation of the machine without the lattice hold. And for good measure, we took the data blindly. So when we unblinded, we found that the acceleration towards the mass is 33 nanometers per second squared. The theoretical value was 36. That provides yet a new limit on this chameleon force. You could now ask yourself, can we do that to test more general 1 over r square fifth forces, right? And people make these plots where they say, here's the length scale of an interaction, and here is the strength of an interaction. So what this plot says essentially, at something like 30 microns, I can currently rule out an interaction that's as strong as gravity at 1 sigma. But at 10 microns, I cannot rule out such an interaction, right? And if we took our lattice interferometer and optimized the geometry for such tests, we would cut into this parameter space. What I want to do with this, however, is to make some inroads into the question, is gravity quantum mechanical? And this is, of course, an old question. And in 1957, Feynman asked, if I can put an atom or a mass into a superposition of being here and here, which way does its gravity pull? If it was a Coulomb interaction, I would say, well, of course, the electric field is in a superposition between pulling here and here. And by detecting the electric field, I can find out where the thing is and collapse the superposition, right? So with electrostatics, that's easy. For gravity, you might expect the same answer, but it's not so easy because we think that gravity is described by general relativity, and there's no straightforward way to quantize general relativity. So we're between a rock and a hard place. Either gravity is classical, as described by GR, but then which way does it pull, here or here, right? Or gravity is quantum, but we don't know exactly what that means. Lots of caveats with this statement. I'll mention only one. Of course, you can quantize gravity in the weak field regime, right? And then there's no problem. However, because you're restricted to the weak field, that means that such theories are at best approximations, right? What is clear, however, is that nobody ever did the experiment. So we want to do that experiment, and Dan Carney and Jake Taylor had the idea that this is surprisingly testable because I can see whether gravity can mediate entanglement. Suppose I have my atom here, and I have a macroscopic, for example, torsion pendulum here. So the atom pulls it that way. Now I put the atom here all of a sudden. The oscillator gets pulled down a little bit and starts swinging, okay? That means by observing the position of the pendulum, I can now tell where the atom is. But in an interferometer, if I know which way my particle takes, then the interferences stop happening, right? So, or in other words, part of the information about the quantum system leaks out into the oscillator, and that means it's no longer in the atom interferometer, and that means the visibility of my atomic interference fringes will go down. But after half a period of the pendulum, the mass is back where it was, regardless of where the atom is. So now the information is back in the atomic system, and the visibility should go back up. Okay. So that would be the quantum prediction. If gravity can be in a superposition state and therefore can mediate if it can be in a superposition state, then the information oscillates between being inside the atom and being shared with the pendulum, and that leads to this collapse and revival of fringes. Okay. But if gravity can only be classical, then that would not happen, and we would only get the collapse, okay? Because the information could leak out but could not come back in. So there's a collaboration with Dan Carney and Jake Taylor generously funded by the Heising-Simons Foundation to set up an experiment to make some inroads here. So first of all, we improved the vibration isolation by having seismometers and active feedback to make the coherence of our system much better. We'll have lower atom temperatures due to evaporative cooling. So if any of these two things pan out, then our coherence splitting product should get much better. The new vacuum chamber has room for a torsion pendulum here that's built by our collaborators at NIST. And other than that, the experiment will proceed pretty much as before. There will be a frame that holds the thing. So what do I want to say? Am I claiming that this experiment can really provide an experimental signature for gravity being in a superposition? No, of course not, right? What I hope to achieve is that someday somebody will build an experiment like that, which will show that gravity can be in a superposition before my graduate students graduate. Thank you very much for your attention. Hi. Yeah. We're shooting for 20 seconds in the first iteration. So yes. Yeah. And so the question is, what is the contrast of this collapse and revival? What's the modulation of the visibility? And depending on how the experiment is set up, that either goes like t squared or even t to the 4. The t square scaling is more favorable. And so in the current iteration that we're building, we're not trying to prove that gravity is quantum, right? We're trying to shoot for 20 or 30 seconds, get really fringes with good signal to noise at that time. And that would hopefully show that basically the apparatus works. And then we might be able to do a second iteration where we improve things further. At the same time, the theorists are working on what models can you already rule out with a very modest performance that we're shooting for right now. And there's one strawman theory of gravity. I say strawman because nobody would believe in it. But surprisingly, it's compatible with experiments right now. And that is, suppose I simulate I couple classical gravity to quantum matter by measuring where the object is and then generating a classical field pointing that way, right? That would, of course, cause a lot of decoherence in the quantum system, but could simulate the effect in experiments conducted so far, and that could be ruled out already in the first generation. So that's what we're shooting for right now. Yeah, so journey of 1,000 miles starts with the first step. That's what we're trying. That's all I'm claiming at this point, right? Yeah. Uh-huh. Yeah. What I mean is, what if the gravity originates from a mass that could be here or here, because the mass itself is in a quantum superposition? Yeah. So, for example, if I had an electron that's in a superposition of being here or here, then the electric field generated by that electron would also be in a superposition. And by measuring the electric field, you would have a 50% chance of finding it pulling there or there, right? And the question is, can I do a similar experiment with gravity? Yes. Yes. Exactly, yeah. I didn't want to use fancy language, but that's exactly it. Can gravity mediate entanglement? That's another way to pose the question. That's right, yeah. So, yeah, so you're exactly right. If I could have the atoms in the ground state of the lattice, then a deep lattice might actually be favorable. The problem with doing that, first of all, in our current experiment, we cannot do that. Even if we could do it, that would generate a sample of large density, and then we'd have to fight atom-atom interactions. I have to admit that, unfortunately, we're still using cesium atoms, which are kind of the worst atom if you're worried about atom-atom interactions. For this new project, we scratched our heads, should we really be using cesium? But then we want to deliver results soon, and so we said, let's not change the species. So we will not condense the atoms all into the ground state so that we are not worried about density effects so much. But you're exactly right. If you could have the perfect experiment in the world, you would go for some with negligible interactions, and then you would probably want to go down all the way to the lattice ground state.
A follow-up question to Leo's. So why does that observation necessitate quantizing gravity? Like, I understand how it would imply that a gravitational interaction is mediating the exchange of energy and therefore results in entanglement between two oscillators. But why does it imply that gravity is quantized?
So I want to say the claim I'm really making is it would show that the gravitational field can be in a superposition. Whether or not that also implies that gravitons exist and they are ladder operators and so on, I have no opinion about.
Okay, sounds good. That clarifies my question. Thanks.
I want to say, though, that Jake Taylor and Dan have an opinion, and they say the one thing implies the other thing, but I don't know why they think so.
Me neither.
No, they are more smeared out. So let's look into the lattice from the top, right? And an atom at non-zero temperature describes some orbit inside that trap, right? And the hotter the atoms, the larger this orbit. So if all atoms were not moving very much, then these orbits would be very small, and there would be very little difference between the phase accumulation in one atom and the other. Now, if the atoms are hot, then an atom in an orbit like that accumulates a different phase from an atom that happens to have a smaller orbit. Okay, even that would be harmless if the orbit in the other lattice side would be exactly the same. But if the lattices are not exactly symmetric, then I get a phase spread between the atoms that's proportional to the degree of asymmetry in the lattice and the degree to which one orbit is much larger than the other. Sorry, there's probably a simpler way to say that. Yeah. But, okay, good. Thank you.
Where
Is that a question about the clock interferometer a la Pikovsky and so on? Oh. So our experimental scheme relies on the gravitational field generated by the mass of the atom, which is only very little changed by bringing it into an excited state. So I don't think there's a straightforward way to use that in our experiment, but I know from talking to you before this talk that there may be ways to get more creative, right? But I think our scheme would not benefit from something like that. Maybe one can come up with a fancier scheme that does benefit. Yeah.
It's 5:01, so let's end it there and thank Holger once more.
Okay, thank you.